Well, my name is Herbert Owen. I guess that most of you know me. I'm from the beginning of the EoCoE. And I will present you the work that we have been doing with Alya for wind energy. So a very brief introduction to Alya in case some of you don't know it. It's a multiphysics code, HPC multiphysics code developed at the Barcelona Supercomputing Center where I work. And it is designed for engineering problems in general, and in particular in cases which have complex geometries, and we typically use unstructured meshes. So its scalability has been tested up to 130,000 cores. It is part of the Unified Application Benchmark Suite, European Application Benchmark Suite. It uses a finite element discretization, and it can solve fluid mechanics problems, solids problems, thermal coupling, and other problems. So within EoCoE, we are working in two main problems using LES, that is large eddy simulation, world model large eddy simulation, and we are dealing with two main problems. One of them is full rotor simulations, that is simulating a real wind turbine with the rotating blades. You have part of the mesh that is rotating and the other part of the mesh that is fixed. And the second problem is the flow over complex terrain. And on the right, you can see a simulation. This is from a recent benchmark, the ALYS benchmark, where actually we have coupled our CFD simulation with forcing coming from the mesoscale models. These mesoscale models are the ones that are part of the package of Meteo for Energy. But this does not come from Meteo for Energy, it comes from the benchmark people. So our LES simulation is based on a model that tries to conserve energy. So we use a simple Galerkin discretization in finite elements with a Runge-Kutta free discretization in time. For the convective term, we use an EMAC form that conserves not only energy, but also momentum and angular momentum. This is a very recent work, less than 5 or 6 years. And then to use equal order interpolation for both velocity and pressure, we resort to a non-incremental fractional step method. And finally, we couple all of this with an explicit subgrid scale model. The one that we prefer most is the Breman model, but we also have others such as Whale, Smagorinsky, and whatever. So typical computational mechanics code has like two main parts. One is the assembly of a right-hand side matrix or right-hand side and or right-hand side. And then if you have some part that is implicit, in our case, we are dealing with incompressible flow, and so the pressure is treated implicitly, you need to have the solution of a linear system. So I will first start talking about the first part, the assembly of the right-hand side in this case, and how we have ported this to GPUs. We use, you have like two options. One of them is OpenACC, that is the one that we are using because it is simpler to read, develop, and maintain. And this is a part of the code where lots of people are working. And so for the moment, we are staying with OpenACC, that I would think is easier. And then you can have CUDA. We have been doing some tests and we can be twice faster, but then it's much more difficult to develop for all of the team. So, well, for the moment, we are with OpenACC. And how do we do this? I cannot explain all of the details, but typically in a finite element code, you have a loop or over all of the elements that form the mesh. And for the GPU implementation, we work with groups of elements. We do these groups of elements of size, vector size, we call it. Typically, the number that is working best for us at this moment is 128,000 elements at a time. This is the most efficient way of doing it. So moreover, on top of our GPU implementation, we have a co-execution approach. What do I mean by this? We mean that we try to use not only the GPU but also the CPU. When you have a GPU supercomputer, you also need to have a CPU part. The GPU cannot work alone. And in typical GPU implementations, this CPU is left idle most of the time. And we have tried to do this co-execution where part of the work is done by the CPU, not a big one, but well, it takes some work from the GPU. So if we have a typical node, say 12 cores, 3 of them offload their work to the GPU, and the other 9 do a small part of the work. Obviously, the GPU is more powerful, so you have to partition accordingly. You have to send the big subdomains to the GPU and small subdomains to the CPU. We have a dynamic load balancing approach that allows us to obtain an optimal balance. Yeah, iteratively, we repartition several times using space filling curve. And in this way, we get to an optimal load balance that makes this efficient. So what have we seen? We have seen that we can scale correctly up to 2 million unknowns per node. And we see that if we use this co-execution approach, we can be 5 times faster than if we only use the CPU. Instead, if we use the pure GPU approach, we are only 4.3 times faster than if we only use the CPU. So there is an 18% gain by using this co-execution approach at the moment. These tests have been done at the Power 9 cluster that we have at BSC. This has Power 9 CPUs plus 4 NVIDIA GPUs. So another topic that I'm very interested in is node level optimization. And we have the luck here at EoCoE that we have the FAO team that I would say are one of the leaders worldwide in node level optimization. I'm very happy to have their help. And so they have been looking at our code, especially at the assembly part. And for the CPU, they have found that our code is not memory bound, and this was a bit of a surprise to me and for the people that work with me. Typically, you expect an unstructured grid code to be memory bound. They have done some improvements around 20, and we see that we can run at 25% of the ABX 512 peak, and these, I understand, are quite nice numbers. In the GPU, instead, they find that the code is strongly memory bound, so there is a very totally different behavior in the CPU and the GPU. There is low occupancy and low memory parallelism at the GPU, and so there is still a huge potential for improvement in the GPUs. So how do we see this in our normal runs? We can run in this Power 9 machine that we have at BSC, and we can also run in Mare Nostrum, that is a typical Intel Platinum cores that are quite typical, a typical Intel for a supercomputer. So what we see is that the times are more or less if you run in one Power 9 node or if you use 2 Mare Nostrum nodes. If you look at the power consumption of these 2 machines, and why do I look at the power consumption? Because I believe that power consumption is perhaps the most important thing in going towards exascale. We see that one Power 9 node takes 1.7 kilowatts, while 2 Mare Nostrum nodes take 0.5 kilowatts. So at the moment, we are still more efficient running on the CPU than on a GPU. And well, this is not what is expected in going towards exascale, and we have still work to do. If one looks at the energy consumption, they are peaking the top 500 list, and we look at the consumption per node. A GPU machine similar to Power 9 should be 3 times more energy efficient, and we are 1.7 times less efficient. So we need like 5 times of improvement. I would like to have 5 times of improvement. So, well, the FAO team is helping us a lot in this direction. They have been recently working on the GPU implementation, and they have started from what we have, and they have measured times. And with our OpenACC implementation, they have timings of 600 milliseconds. And they have been able to optimize this with OpenACC, and they have reduced the times to 175 milliseconds. This is 3.5 increase. Moreover, from what they have explained, I still haven't seen this, they have been able to do kind of some automatic translation to CUDA. And when compiling this CUDA, they go to 53 milliseconds. This is an 11 times improvement using CUDA. And well, if we were able to translate all of these improvements to Alya, we would be in an excellent position in the GPUs. And the advantage that they obtain by using CUDA is higher than the one that we had experienced, at least 2 times. And this would be a good reason to go to CUDA. And moreover, if we can do this kind of automatically or kind of transparent for the developer, this would be ideal. So I'm very optimistic about this work that they have been doing. A small comment on the ARM machines. In Barcelona, we also have a small ARM partition. This is kind of a mini Fukaku, the same chips, but at a much smaller level. And we also have the Fujitsu compiler, but we have not been able to compile Alya with the Fujitsu compiler. And this, I understand that is work that needs to be done in the Fujitsu compiler. And this will be, I don't know, this is perhaps related to this co-design that we have to give feedback. And one of my feedback would be that we need better compilers, especially for these ARM machines. We have compiled with the GNU compiler in this ARM machine, but then it's not competitive against Intel CPUs. Now going to the second step, the solution of the linear system. As I mentioned before EoCoE, we relied on in-house code, and we have the typical Krylov solvers, Chenres conjugate gradient, and even deflated conjugate gradient. And I have this figure from perhaps one of Alya's most cited papers, where we see that that as the mesh is refined, the number of iteration increases, and this is a well-known problem with these Krylov-based solvers. And in order to avoid this, we are working with the different solver experts within EoCoE. Here, I will present the work that I have been doing recently with the PS Blast team. So we have been using AMG for PS Blast, an algebraic multigrid tool within PS Blast or companion of PS Blast. It's very nice to say that for the moment we have tested only their CPU implementation, but they also have a GPU implementation that as soon as we finish testing, doing this test, we will pass to the GPU version. So where have we tested this? We have tested this in a real wind problem. This is the balloon benchmark. It's kind of a cliff where you have the incoming wind. And so we will do a weak scalability study that is perhaps the most important thing for a linear algebra package. And we start with a mesh with 32 million elements, and we apply an automatic mesh subdivisor. That means dividing the element into elements with half the size. This means you have 8 times more elements in 3D. We apply this subdivisor twice. This is a 64 times increase in the number of unknowns to go to 2,000 million elements and 358 million nodes. So, and here I present some of the results that we have obtained. We have the mesh with 0 divisors. We tried with 3 different number of unknowns per core that is running in 48 cores, 96 cores, and 192 cores. We look only at the highest load per core. Then we apply one divisor and then a second divisor. The one first observation is that when we apply this mesh subdivision, we have elements that are smaller, but the number of iteration remains the same in going from 0 divisors to 2 divisors. This is an excellent result that we didn't have before with Alya. There is a bit of increase in the number of iterations with one divisor, but this is not worrisome to us, especially if it goes down again to 4 when we apply the second divisor. And then the second point that is the key one is that the CPU time does not increase significantly. We are going from 0 divisors to 2 divisors, and the time goes from 0.67 seconds to only 0.72 seconds. And this is excellent results for Alya, a huge improvement for Alya. If we look at the times in this same problem with Alya's own solver, in the case with 0 divisor, Alya is only slightly slower than PS Blast. But when we go to the 2 divisor case, Alya is 3 times slower. So this is a very nice improvement that we have obtained. So finally, I would like to talk about the use of external libraries. In this case, I have been talking about PS Blast, but as I mentioned before, we have interfaced with most of our a great part of the linear algebra packages available in EoCoE, not only PS Blast, AGMG, Mafis, Pastix, and MUMPs. In the past, as I said, it preferred not to rely on external libraries, only perhaps Metis for the mesh partitioning. We have integrated 5 different linear algebra packages. And moreover, we have also integrated libraries available through EoCoE for input-output and also for fault tolerance FTI. And we have interface Alya with PDI or through PDI with Sensei, Adios, and Catalyst. This is the talk, very nice talk that Christian gave this morning. And I would say that the interfacing efforts are small for the improvements that we have obtained. So we have presented this in several congresses this summer. The West Congress, this is on with energy. In the PAR-CFD, we had 2 presentations, one on the solvers given by me and one by Guillermo on this co-execution approach. We will also be presented at the ISC 21, where I am hosting a mini symposium, where also people from the Water Scientific Challenge will be presenting. And finally, Christian will be presenting this work on in situ visualization that he presented here before. So conclusions, I would say that we have done significant improvements, but well, there is still lots of work to be done. One of these areas where there is still lots of work to be done is the GPU implementation. I would say that computational improvements are needed, but they also need to be accompanied by physical modeling improvements, and we have very little resources for the physical part in EoCoE from my point of view. And it is important to benchmark these results against experiment. And also, I would like to say that the data, the experimental data is quite scarce in cases for complex terrain. As a final point, I have this drawing from my son, and I'm a bit worried about this. He draw our family, and you have my wife and him playing in the sofa while I'm working in the supercomputer. And I want this to change. I'm trying to learn more about the politics at the European level. I have found that there is a similar project to the wind part of EoCoE, only to the wind part. And if you look at the budget, it is at least 1 order of magnitude higher than what we have for doing these 2 same things that we are doing, flow over complex terrain and full rotor simulations. So I know this is a message I want to transmit somehow to the European community, because we are falling far behind in HPC for wind energy compared to the United States. So, well, thank you all. Thanks to the people that have helped me, the team from FAO in optimization, the team from Jülich in visualization, the people from BSC that have helped me, and the team from Italy that has helped me with the linear algebra solver. Well, so thank you all of you, and obviously thanks the Horizon 2020 grant that enables EoCoE.
Thank you very much, Herbert. I think the message is heard loud and clear. Does anyone want to ask Herbert something? Okay, I have raised hand from Mathieu Loubet.
Yes, I hope you can hear me well.
Yes, we can.
Thank you. So Herbert, I have a question. Do you have examples of what the team of FAO did to improve the OpenACC version? Do you have concrete examples?
I don't know what you mean by examples, but I have a description of the main changes they have done, and I have the two mini apps, the original one and the corrected one. And so, well, I will go into technical detail from my capacities, and if the FAO people thinks that I'm saying something wrong, please correct me. So, as I said, we work in these groups of elements. We do lots of elements at the time, 128,000. And then, so we have to get to memory these 128,000 elements, the data related to these elements. And then we do operations with these, and we come to a right-hand side for all of these elements. And so there are several areas, there are some arrays that are the input ones, then we have the output ones, but there are some arrays in the middle that are work arrays, yeah? And we had them the dimension of size 128,000, yeah? With this idea that everything works. But they saw that this introduces a burden on the memory. So the memory, from what I understand, has to be written intermediately a lot of times. And so they changed this to scalars, not vectors of 128 characters, but scalars, and they put it as private in the OpenACC. And this, I understand, is the main difference that we had not realized. So the memory now works much better. And then we have some initializations to 0, and they also put them closer to where we are going to use them. And this also has saved significant time.
Okay, thank you.
Thank you. Ulrich, you wanted to ask something as well?
Herbert, very nice. Just a quick technical question. What percentage of the Alya runs does typically go into the linear algebra?
Which is the cost of the linear algebra compared to the total cost?
Yeah,
well,
roughly.
This depends on several factors. Perhaps one is the size of the problem, especially with Alya's own solvers, because if we don't have a correct weak scalability, then the part of the assembly scales nearly perfect. There is not much challenging in scaling the assembly, while scaling the solver is much more complex. So as you go to bigger problems, the percentage that goes into the solver is bigger. And then the other key factor is the anisotropy of the mesh. So if you have isotropic meshes close to the boundaries, then the solver likes it a lot, and the percentage of the solver is quite small. Yeah, it could be just 10%. But when you have anisotropic elements and not highly anisotropic, if you have highly anisotropic, the solver tends to dominate. But in LES, you cannot have highly anisotropic. In LES, we have with some anisotropy, but this also introduces difficulties to the solver, so your CPU times a percentage in the linear algebra part can be bigger. So I would say that in LES runs, this would be around 30% to 10%, but and it depends a lot on the mesh. If we want to do something related to runs, and here in EoCoE, at this moment, I am doing nothing with runs. We are focusing all on LES, but we also work a lot with runs, and we have this very nice collaboration with Iberdrola, where we use run simulation. This is the standard nowadays in the industry, and there the solver is very expensive. And in the future, we could try to do some runs LES, put runs close to the boundary to have something better than a wall model. And then perhaps this balance could change again.
Thanks, Herbert.
Thank you, Herbert. Thank you. Thank you, Rich. Is there something else? Yes, Michel Raskin.
Yes, I have a quick question. Thank you. I was wondering if you have any plan to support other architecture than the one based on NVIDIA GPUs.
I don't understand the question. Sorry.
Well, you mentioned that you pay a lot of attention to the maintainability of the code, which is critical when you have a lot of people, many developers like you. I was wondering how you will handle, what are your plans to handle other GPU machine like the one based on AMD, which is also coming on the market right now?
Well, I don't know. I understand, but I'm not sure about this, that OpenACC should be open, but I'm not totally sure if OpenACC works in an AMD machine. Obviously, CUDA would not work, so we would have to port this to OpenGL. Well, I don't have an answer for this. I would need to. I'm mainly on the Win side. I understand things from the GPU side, but yes, it would be nicer to have something that is more automatic. I don't know. Our code is Fortran, so at the beginning of EoCoE2, we were proposed this idea of trying Cocos, that now it doesn't seem to be the most efficient way to go, from what I saw in the talk from Water for Energy. I don't know yet, but most probably we would have something that can do OpenCL in the future also. I don't know if something like, I don't know about, I understand that the other possibility is going to something like Cocos, or having some Python scripts that automatically generate code. From what I have talked with the FAO team, there is another team within FAO that they have some kind of automatic code generation tools. But well, due to budget restrictions, this is not possible to be treated in EoCoE2, and we will discuss if we might be interested in including this in EoCoE3, and this will depend mainly on Guillaume Rousseau, that is Alya's main developer.
All right, thank you.
Thank you very much, Herbert.